The next property that we're going to talk about is when we have to introduce derivatives in our g function. And so I need you all to go back in your notes to the places where we left blanks. First in the approach, just reflecting back on what we did in this problem right here. Sometimes people are a little bit like confused about which terms we group together and why. So there might be a temptation to group like all the A terms together, all the B terms together. So I just want to make a note in that approach that what we're trying to do is make our solution work for all x values. Because y is a function of x, so it should always be true, no matter what x value we're at. That means that when you start setting up your equations, you don't want to see x's anymore. That's why we group by terms that include x. That lets us kind of cancel out like that there's an x squared because we set the two x squared functions equal each other, or groups equal each other. That's one of the main sticking points in this section, so I just wanted to make sure we kind of emphasized it here. And then once you've got that written down, we're going to move to the next set of steps. So pause if you're still doing this. But I had told you that we would fill these in with different rules that we use to find what g should be. And so we're going to do the second rule, which, as I've indicated in our little outline here, is going to be related to derivatives. So our second approach, B, is going to be to use derivatives of terms in g of x. And you do have to do like all three of these all the time. It's just in our first example, we didn't, it was like picked, so we didn't have to worry about it. So an example where we would have to worry about it would be, I'm actually going to take away that -1 now. But suppose we were just doing y double prime minus y prime equal to 2x squared. Following like part A, we would say, okay, I guess g1 is x squared because I see an x squared type term over there, which is true. We definitely want to include that function. But then we also want to include all the possible derivatives of that function. So when I take derivative x squared, I get x, or 2x, so I use the function x, the simplest possible version. And then when I take derivative x, I get 1, so I use the function 1. So even though on this side I had 3 terms, and on this side I only have 1, I'm still going to end up with 3 g's that I add to my problem, because I need to consider all the possible derivatives that I might be introducing when I start to take y sub p and plug it into that differential equation. We're going to do an example that looks like this. I've been flipping all over the notes, so I want to make sure I get to the right place. Yep, there it is. And then I want to move the outline, which always takes a couple seconds. Let's you all catch up with writing. So our example that's going to show how this works is going to be thinking about taking y double prime minus y prime plus y equal to 2 sine 3x. Note for us is that y double prime minus y prime plus y equals 0 has solutions y1 equal to e to the 1/2 x cosine root 3 over 2x, and y2 equal to e to the 1/2 x sine root 3 over 2x. And again, you would find that using the constant coefficient approach if it wasn't given to you, because we'll need it to write our general solution. to find y sub p, we note that our g is that right side, 2 sine 3x. And so my y sub p, I want to introduce my undetermined coefficients like a, take the function of x part of g, so that's going to be sine 3x. I ignore the 2 outside because it's a constant. It acts just like a, so it would make my life harder to keep it around. I cannot ignore the number that's inside sine. It's like what's connecting x to sine, so that type number does have to stay. Anything that's like an argument to a function of x, keep it where it is. So that I get from thinking about part A, what does g look like? Now it's in y sub p. But then our new thing is that we also include derivatives. And derivative of sine is cosine. So part B tells me that I need a second term that looks like cosine 3x. And then I would keep going until I covered all possible derivatives, but since sine and cosine flip back and forth between each other, I'm done. Derivative of cosine would be sine again. I already included sine, so I just need these two terms. But just remember that you do need to make sure to include all the derivatives of y sub p, even though in this example we only need the first one. After that, I want to plug y sub p into my differential equation, which means I need to take the derivatives. So derivative of sine 3x is going to be 3 times, oops, that a stays where it is, and then sine becomes cosine 3x. And derivative of cosine throws a negative. Since there's 3 inside, I go ahead and multiply by 3, b, and then cosine switches to sine. Yep, that's my first derivative. And yp double prime, I just take another derivative. So 3a cosine 3x, I get a negative out of switching cosine. I get multiply by 3 again from what's inside. Then a and cosine switches to sine. And taking derivative of 3b sine 3x, which I forgot to put the parentheses around, sorry about that. I've got the negative stays, 3 times 3 is 9, b, and then sine switches to cosine again. And we're going to plug this into our differential equation. And I'm going to show the steps of doing that, but if you wanted to just sort of, I'll tell you when we get to the final version of the equation that we're going to use. You might want to only copy down that version. And in your skeleton notes, I only wrote that last version. Just because these problems aren't necessarily super complicated when we're plugging them in, it just can be a lot of terms that we simplify together. So I need my yp double prime minus yp prime plus yp. So my yp double prime is minus 9a sine 3x minus 9b cosine 3x. My yp prime is take away 3a cosine 3x minus 3b sine 3x. And then my plus yp was not given enough room to exist, is going to be plus a sine 3x plus b cosine 3x. So that's just plugging in yp to the derivatives. Yp double prime, yp prime, yp itself. And then I'm going to have to group these by things that look like the functions. So this is the part that I would recommend you all actually put down in your notes. So I want the sine terms. I'm going to go ahead and underline all my sine terms. So I've got minus 9a from that first one. And then in the middle here, this is going to be minus 3a cosine 3x plus 3b sine 3x. Please make sure you distribute those numbers all the way through. That means that I need to have a plus 3b right here. And then from that last one, I just have a plus a. And then I also need my cosine 3x terms. I'll do the squiggly underline for those. So that's going to be minus 9b from the first, minus 3a from the second, and plus b from the last. And all that is equal to, on the left side, just 2 sine 3x. And this one's a little bit trickier because since g didn't have all the terms that we introduced to y sub p, it doesn't look like everything that's on the right side. So you're always going to have to make sure to note that 2 sine 3x is the same as having sine 3x times 2. That part's the same. But then this cosine 3x that we introduced, that does exist, it's just equal to 0. Anything that doesn't show up on the left becomes a 0 equal to whatever multiplies that function on the right. So I'll need to move to the next page to write the resulting equations. Pause if you're still working. This gives us 2 equal to the sine type terms, minus 9a plus 3b plus a, and 0 equal to the cosine type terms. That was minus 9b minus 3a plus b. And just simplifying those, this becomes minus 8a plus 3b and minus 12a plus b. No, oh, sorry, I combined b's and a's. I combined these two for an a term for some reason. It's minus 3a minus 8b, my mistake. And then we want to just solve these for a and b. This is one where I prefer to work backwards because I like the ones that are equal to 0 more than the ones that aren't. So 0 equal to minus 3a minus 8b tells me that b is equal to 3a over 8. And then I'll plug that into the more complicated one. 2 equal to minus 9a, sorry, minus 8a plus 3b is plus 3 times the thing I just found, 3a over 8. And I can go ahead and work on simplifying that, minus 8a minus 9a over 8. Or I want to combine those into one fraction that's divided by 8. So up top, my minus 8a becomes minus 64a, because I have to multiply by 8 to add it to the fraction, minus 9a, which is minus 73 over 8 times a. That's equal to 2. So when I move that fraction over, I get that a is equal to minus 2 times 8 divided by 73, or minus 16 over 73. That means that b, which was 3 over 8 times a, is going to be 3 over 8 times negative 16 over 73. 8 and 16 cancel out to just be 2 on top. So I've got 3 times 2 is 6 over 73. I do know that algebra can be rusty for some of us. Algebra can be rusty for me. If you think I make some mistakes in these videos, I make many more when I'm trying to do algebra as I talk. So just be careful when you're doing these. You can always like plug your numbers back in and make sure they work to know that you got the right answer. And if you ever had to solve like 4 equations for 4 unknowns, if you've taken linear algebra, you know the easiest way to do that on paper. And if you haven't, I'm sure you know how to look up a calculator online that could do that and make sure that you got the right answers. So use the tools at your disposal when you're alone, the tools that are allowed by the syllabus. And then when we take exams and stuff, I promise we're going to stick to the simpler equations. So I know this video is getting kind of long, but I just want to note that this gives us y sub p was that a sine 3x plus b cosine 3x. So that's negative 16 over 73 sine 3x minus 6 over 73 cosine 3x. Messy, but a function. And then our general solution is y equal to c1, the functions I gave you to start, e to 1/2 x cosine root 3 over 2x plus c2 e to 1/2 x sine root 3 over 2x. We just do c1 y1 plus c2 y2 plus y sub p, and that's where we just add the thing we found. So it's minus 16 over 73 sine 3x minus 6 over 73 cosine 3x. And at this point, we've found the solution.